Welcome, my friends. We are talking about uncertainty and significant figures in the world of IB physics. It doesn't get any crazier than this, and we're going to be talking about quite a bit of stuff, as you can see all along here. So we'll move kind of fast because none of it's rocket science. I will make some assumptions that you know how to use scientific notation and how to use some prefixes where you can turn meters into kilometers and you can turn grams into kilograms, etc. Some people wonder about what prefixes you need to know, metric prefixes, not necessarily metric. Probably for your everyday life, you need to know kilo, mega, giga, and tera. And then down the smaller ones, you don't need deci, but these here are the ones that you need. The others are nice to know, but it's kind of academic exercise. As you take measurements in a lab situation, many of your measurements are going to be wrong. You're going to have what we call some systematic error, or you're going to have some random error. Now, the systematic error is going to be something that's going to make your values be often too high, or they're going to be all of them too low, but you're not going to have them either too high or too low. An example of this, let's say you have a probe that is not calibrated. Many people would have a scale, maybe a bathroom scale, that always reads everyone's weight or mass as maybe 1 kilogram too high, or maybe it always reads everything 1 kilogram too low. Now a random error, on the other hand, is going to make you randomly high on one measurement, then the next measurement might be too low. And in most of the lab situations, you're going to have random errors. Systematic error I see in high school students' labs is a much less common error to have. And one thing that almost always gives you random error is when you're using a stopwatch. Bloop, bloop. If you're just timing someone, sometimes you stop it too early, sometimes you stop it too late. You're going to be all over the place on that, making it random, sometimes high, sometimes low. Now, with precision and accuracy, you want to think of precision as meaning how repeatable a measurement is. If you take lots of measurements and they're all measuring the same value, then that means they're quite precise. You can think of accuracy as meaning how close your measurements are to what the true value really is. So take a minute and pause this and try and match up these 4 diagrams with the correct description of accuracy and precision. Now, hopefully, you said that this one here was both accurate and precise because they're all at the same place and they're all on the target. This one is neither accurate nor precise, and this one is precise because they're all the measurements or shots as you hit the target are in the same spot, but they're not actually hitting the center of the target where you want to be. And so this one is accurate because if you took the average of all these measurements, they would give you an average in the middle of the target, but they're not precise because they're all in a scattered area. So let's say you've got a pendulum, glook, glook, and a stopwatch, and you're doing an experiment where you're timing, measuring the length of the pendulum and how long it takes for the time of one swing. So let's say you measure a certain length, but you time it to be faster than it should be. You have a random error where you've gotten too quick of a time, and you're off significantly from what the actual value should be. What you then do is you take another measurement, and maybe your other measurement is right on. And then you take another one at the same length, and maybe it's too high. And then maybe another one's here, and then another one's here, and then one here, and here. And you keep taking these measurements, and you get all these different values. If you then average them together, that reduces the effect of the random error. And so what you want to know is that you can reduce that effect by taking many measurements and average them all together. When you do a calculation with multiplication or division, you have to know how many significant figures are going to be in your answer, which is really easy with multiplication and division. Here's the rule right here. And then if we take this number and divide it by this number here, the calculator spits out this. See if you can figure out, pause it, what the actual correct rounded number would be. hopefully you applied the number, and you said, or the rule, said that this had 3 sig figs, and this one had 2, so our answer is going to be 2. So I round it to 24, and I get rid of all of these other numbers here. For addition and subtraction, dealing with sig figs, it's a little bit trickier. Here's the rule right here. Now, for example, let's say I'm adding up this number and this one. What you want to do is you want to look and say that this first number, these are not significant. These two here, but this one is, so it's significant to the hundreds. This number is significant out to the tenths place, so it's a more precise value than this one. But since the tens column here has no sig figs, I cannot round, or I cannot have values past the hundreds column. So what your rounded answer should be is 26,100, because I'm limited by the hundreds column because these out here are not significant. Notice that this had 3 sig figs and this had 2. You can't just count the number of sig figs. Here, you go to 157. These are significant to the ones, and so it stays significant to the ones. Notice it's funny that this had 2 sig figs, this had 2 sig figs, and this now has 3. So you can gain significant figures when you are doing addition and subtraction. In most of the lab measurements that you take, you're going to want to express how much uncertainty you have in that measurement. And maybe the simplest type of uncertainty that people can understand is an absolute uncertainty, where you give your value, let's say in grams, and then you say you have a plus or minus of so many of that same unit. That's your absolute. Now, your fractional uncertainty and your percentage uncertainty, for fractional, what you would do is, for your uncert, you would take the 2 grams and you would divide it by the 88 grams. And if you work that out on your calculator, you're going to get something like 0.0227. And you always express a fractional uncertainty as a decimal. It's actually not very useful, this fractional uncertainty. The more common way to do it is you take that fractional uncertainty and you express it as a percent by multiplying it by 100. So this is 0.02. This rounds to about a 2% uncertainty. If you have 2 lab measurements with absolute uncertainties and you have to add or subtract those values, the rule is very easy. Here's the rule right here. Basically says you add the absolute uncertainties together, even if you were doing a subtraction problem. So for example, pause it and see what length you would get with combined uncertainty if you add these 2 rectangles together. Hopefully, you got 225 centimeters plus or minus 1 plus 2, or your 3 centimeters. It's just that easy. When you multiply or divide lab values with uncertainty, it gets a little tricky, because the rule, if you look up here, is that you have to add up the percent uncertainties. So take a minute and pause it, and for this rectangle, try and solve for the area, the percent uncertainty, and the absolute. And hopefully you got that the area, when the calculator is going to spit out 14,454 square centimeters. But you have to realize that 1 out of 73 centimeters is going to equal about, I got 1.4% uncertainty. And this value, 3 over 198, is going to be a 1.5% uncertainty. So you add 1.4 plus the 1.5, and you're going to get about 3% uncertainty. So that goes right here. And then if you want to take 3% of your 14,454, that's going to give you like a plus or minus of 433. So what you can express this as, round that to the hundreds, round this to the hundreds, and you get something like 14,500 plus or minus 400. This is all in square centimeters. The end. Woo!